Namaste and a very warm welcome to all the registrants for this course on Mathematical Foundations for Machine Learning. This is Dr. Arulalan Rajan. Myself and Dr. Ashok Rao will be the instructors for this course on Mathematical Foundations for Machine Learning. We are assisted by Mr. Gaurav Hegde, Mr. Aditya and Ms. Kavya Sri Kumar. They are our teaching assistants for this course, and this course is basically a 12 weeks course, as you have all seen in the course website. So basically, why did we even want to offer the course like this? So the motivation for us is basically many of us do machine learning. A lot of math goes inside machine learning. In fact, there is also a lot of misconception that machine learning is all about coding. So what we thought was, why not we do a very foundation level course for machine learning which covers basic ideas of linear algebra, probability and calculus and optimization, so that at least people are able to appreciate the nuances of some of the algorithms and the ideas used in machine learning and in data science. On that premise, we thought we would bring out a course which purely focuses on the foundations. We are not going to talk about really heavy machine learning algorithms or ideas, but we want to ensure that these foundations that we give in this course is going to help you understand the ideas of machine learning and data science in a much better manner and appreciate those concepts in a much better manner. So in fact, you would have seen in the course intro video where I had actually spoken about what are the things that we want to cover, and we really want to see like what are the essential topics that are required for someone to learn machine learning and probably become an expert in this particular domain. Most importantly, we must know that this machine learning is more or less like a what do you call it? It has become a common phrase across every domain, and most of the times we also see that there is a lot of mathematics that are involved in it. When you look at any machine learning textbook or probably even some papers, you see a lot of mathematics there with a lot of notations and stuff. And what we see is some of these ideas which are very fundamental to this in terms of mathematics are what we have already done in various other math courses, but only thing is like, how do we tie up these ideas to what we do in ML? And that seems to be another point which we need which really requires a lot of emphasis. So what we are trying to do in this is like, we have put up certain topics which we felt were very essential and central to some of the mathematical ideas which form the foundation stone for ML. And so we made a 12-week course contents, as I said before, which we also talk about some applications and things. So let us get on to see what is it that we are trying to do in this course. Okay. So the first and foremost thing that you would see and you would encounter is like, ML is all more or less a lot of mathematics involved, where the most important math that you would probably require is linear algebra, the idea of matrices and linear algebra and various other ideas from linear algebra are brought on to the domain of machine learning. And another important domain of math that which we really need is the idea of probability, especially the idea of conditional probability and conditioning, which forms central to the machine learning domain, in the sense that you have certain features. Now I want to find out, if I have certain features, do this particular object belong to that class or probably to a different class and so on. So we need to really know about probability and stuff, and it is also about a lot of prediction and classification that we do with machine learning, which means there is always a level of uncertainty, and we want to quantify that uncertainty, and quantifying uncertainty definitely requires knowledge of probability ideas. And the third thing is most important, is the idea of statistics. After all, we collect a lot of data, we train using the data, and then we try to predict. We get a model, ML model, and then try to do prediction or classification. We know that prediction and classification forms the two important what would you call the tasks that we do in machine learning. And in order to train our model, or in order to get the model parameters, in order to get the coefficients of the curve that you are going to fit, we need a lot of data, and a lot of data simply means collecting data, and collecting data simply implies it is statistics. So, we are going to look at a lot of we need to know the idea of statistics. So, statistics form another essential what would you call topic of mathematical topic required in machine learning. Of course, you would see all this optimizations related stuff where you would look at graphs, and you look at functions, you basically try to do data visualization and all those stuff. And then the most important thing is our calculus. All of us would have studied single variable calculus, and then we would have done a lot of interesting stuff. But when it comes to ML, it is no more a single variable calculus, you end up looking at multiple variables, and therefore you need to know the idea of multivariate calculus, which is again going to be used in the context of optimization and stuff. So, our basic machine learning involves these topics and some more. If I were to say, like, what is the math that we begin with for machine learning, and what is the math that we end with for machine learning, I would probably be saying that the math that you would require for learning machine learning is getting into this domain is basically a lot. But we just cannot get sucked into the complete mathematics, because we are also looking at certain applications. What we really need to know is we just need to know the essential mathematical topics which would help us navigate through this domain of ML. Okay. So, here you go, you find that there are 4 important tasks that we do. We look at regression, we look at dimensionality reduction, we look at density estimation, and we also look at classification problems in ML. And all of these probably, if you look at the entire thing is built on foundations like linear algebra, analytical geometry, where we talk about distances. Then we have matrix decomposition, which is basically meant for computations and stuff, vector calculus, which is essentially the multivariate calculus which is required for optimization that is shown here. And you also look at a lot of probability and distributions, which means we must have a strong grip on probability and distributions, and probably on vector calculus, then linear algebra, then of course use all these ideas and then get to the domain of optimization. And analytical geometry, as I said, is also essential, because you need to talk about distance and other metrics and so on. So, if you look at some of the interesting, nowadays anything you talk with memes, it kind of helps you understand better. So, if you look at the World Wide Web, the internet for the machine learning system, look at this. It says, look, this is your machine learning system. Yeah, pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. So, you see the importance of this. Actually captures the true nature of linear algebra as applied in machine learning. And the other thing, look at the statistics. You guys always act like you are better than me. Machine learning, artificial intelligence, and deep learning. There is always there is this thought process which says, look, machine learning is also a glorified statistics and kind of. So, you need to know a lot of statistics and probability if you want to do machine learning. And how nice if calculus was this, where you have a function, the derivative, the second derivative. For example, here you look at this coffee bean, coffee powder, and coffee as such. But unfortunately, our calculus is not going to be like this. Our calculus is going to be much more complicated than what we see here. Okay, cool. Then, so what is the amount of math that you need? This is our representative numbers. It just says, look, you need to know a lot of linear algebra ideas, then you need to know a lot of probability and statistical ideas, then you need multivariable calculus. Of course, you also need algorithms and complexity and the other things which include coding and a lot other stuff. So, what we are going to do in this course is we are not going to focus on the coding part of it, we are going to focus more on the foundational mathematics for ML, as I said before. We are going to look at linear algebra, we are going to look at probability theory, and then we are looking at multivariate calculus and optimization together. We will also look at certain applications as we move, certain algorithms, maybe 1 or 2 algorithms and applications as we move. So, what is the math and machine learning? First of all, you know that when you collect data, you actually put that in a in a single column format for a particular variable. You end up putting the data in a single column, and that becomes a vector. Like the moment you say vector, you already are into the domains of linear algebra and vector spaces and a whole lot of stuff. So, now you collect such vectors and then put them in a table, you end up getting a matrix, and you would see that every column corresponds to so many observations of the single variable, and every row corresponds to one observation of multiple variables, and therefore you basically get into m observations of n variables. So, you end up getting into m by n matrix, and the moment you get into m by n matrix, or the whole ideas of matrix theory and linear algebra kicks in. You start employing all those things and then see what you want to see out of your data. In fact, somebody who has done a very basic course on linear algebra before would actually appreciate that you look at the ideas of bases, you look at the idea of linear combinations and a whole lot of things which actually help you to look at the data and understand the structure that is there in the data. So, we employ a whole bunch of concepts and ideas from linear algebra onto the matrix of data that we have, data matrix that we have. We will see eventually in the detailed lectures, like as we go on, how these ideas are applied, and we will look at the ideas of linear combination, linear independence and a whole lot of stuff. In fact, as I mentioned before, what you normally have is a vector space in linear algebra could actually become a feature space in machine learning. So, playing around with matrices, the moment you want to play around with matrices, you get all the tools from linear algebra and matrix theory. A simple example is like where you look at dot product of 2 vectors. We already know the dot product of 2 vectors from the idea of vectors which we studied in or physics, high school physics or somewhere, where we say the dot product and then you get the cos theta there, like A dot B divided by magnitude of A into magnitude of B is cos theta. And when we say that theta is 0, both the vectors are basically in the same direction, that is what we say, and theta is 90, we say that the vectors are orthogonal to each other. Now, when you say that both the vectors are in the same direction, you actually tell them that look, both the vectors are same. I mean the similarity is high, it means the angle is 0, then you say they are in the same direction. But you say that okay, between 0 and 90 degrees, you say that the cos theta value is like positive, and then you say that look, oh, that is fine, you can use cos theta as a measure of similarity. In fact, you would later study in a detailed machine learning course, you will look at cosine similarity and stuff, where we typically use A transpose B. The A transpose B idea comes from let us say the idea of matrices. I want to figure out what is A dot B, it is A transpose B. A transpose is like the transpose operator is typically you associate with a matrix, you take the transpose. So, I have a column vector and then I make that a row vector using the transpose operation, and then I take A transpose B and then look at what is the similarity and so on. Which means if I want to find out some features and I want to look at some kind of I want to look at 2 documents and then I want to figure out if there is a similarity between the 2 documents, I could actually go for something as simple as a dot product. So, this idea is something which we really want to emphasize on, right. These are essential operations that you do on vectors in linear algebra. you can the other thing is, as I said, like linear combination of vectors. When you try to do linear combination of vectors, you may actually you are trying to basically each column vector is associated with a variable. For example, you already know that the first column of the matrix, suppose I have something like this. So suppose I have A11 x1 plus A12 x2 is equal to B1, and A21 x1 plus A22 x2 is equal to B2. I know that x1 basically scales the variable, the vector A11 A21, and x2 scales the vector A12 A22, and that gives me another vector B1 B2. That means now what I can say is, look, this new vector that I have is basically obtained as a combination of these two vectors. Now similarly, you can get combination of variables, and you get into the idea of features in machine learning, and features are very essential as far as machine learning is concerned, and you look at independent features and so on. And you do use a lot of ideas of projection as far as ML is concerned. The one most important idea of machine learning which employs projection is the dimensionality reduction, where I have data in a larger dimensional space, and what I do is I try to project that data onto a lower dimensional space and see if I can understand the data better. So that is the idea of dimensionality reduction, which essentially uses the core idea of vector projection, and this is a crucial algorithm. This is a very important algorithm as far as ML is concerned, which means now we know that, look, we are going to use all these ideas, and we need to know how these ideas are implemented and what these ideas actually are. In fact, the other thing that you look at is basically prediction. You have collected your data, you have a lot of data. Now based on that data you do training and other things. Now what you want to do is you want to check whether the data that you get, where the object that you get is going to belong to this class or that class. And the point is, like, when you say classification problem, or when you try to predict whether the future data is going to be falling on this particular curve that you fit, there is a problem there. We do not have complete data, and we just only can make some prediction. When you make prediction, you try to basically make informed decision, and you try to do some kind of effective risk management in a business. You want to make a informed decision. It could be as simple as like saying, look, I see that the cloud outside, the weather outside is like a bit cloudy, and I want to know whether I should carry an umbrella with me or not. I want to predict whether it is going to rain or not, but that is a lot of uncertainty involved. So what do I do is I want to quantify this uncertainty, and that quantification of uncertainty basically requires probability. In fact, the other thing is saying like, how much confidence do I have for this belief that it might rain now, and that quantification of confidence is also something which requires an idea of probability, right. In fact, you would also see that when somebody goes for a treatment in a particular hospital, they say that, look, on this surgery there is a 90% chance that the person would be fine, and there is a 10% chance that there could be some issues. So you are trying to now make a decision in the presence of this uncertainty whether you want to go for a surgery or not, and I am trying to use probability ideas to quantify that confidence that I have. And as I said before, given certain features, does this belong, the object belong to this class or that class? So you really have the ideas of conditional probability. And you also have Bayesian classification. A simple place where you use Bayesian classification is like to classify your emails into a spam or non-spam email. And the ideas of random variables are very crucial in the domain of machine learning. You see conditioning of random variables, and then of course most important stuff is, can you find some kind of a correlation between the features, correlation between variables, and then you look at a lot of covariance and stuff. And most of the times what happens is whenever we see that there is some kind of a correlation, we always say that I wouldn't say we always, we are tempted to say that, look, okay, these two are correlated, therefore one could be the cause of the other, which is essentially a very it's a very big blunder that we would be making if it were actually not a cause and effect relationship, a causal relationship, right. in fact this meme that we have aptly captures, it says like, I used to think correlation implied causation, then I took a statistics class and now I do not. Sounds like the class helped. Oh, the reply is like amazing, it says, well, maybe it means you really cannot correlate, when you have correlation you really cannot say that it actually has causation and so on. So how do we, I mean so what is it to say correlation, how do we capture this correlation, does this correlation have any other meaning like the correlation that we use, which is like correlation coefficient that you would have studied in class 12 or 11th statistics, like does that capture any relation which is nonlinear, or is it only going to capture linear relationship, all those things we are going to study here. And the third one is where you train on historical data. It says when you train, what is it to say, training machine learning models, you find out and adjust the model parameters to to optimize some performance measure. You could either maximize the performance or say minimize the error, maximize the profit, you have a lot of stuff there. So the moment you say maximize and minimization, you would have studied in your again class 12 where maxima and minima, finding maxima and minima involves looking at derivatives and second derivatives. But the most important thing is, as far as ML is concerned, this idea of ML in machine learning involves a lot of variables. That means whatever function, the objective function that you are going to optimize, it is going to be a function of multiple parameters. There could be variation of the objective function across multiple directions, and so single variable calculus is not going to help us. So how are we going to look at all that? And that is exactly where we get into the idea of multivariable calculus. And the moment you study multivariable calculus, where we look into the idea of gradients and Hessian and so on, we try to look at, okay, now I have got this, now I know that the function is going to vary across different dimension. What I do is I want to find out the rate of change across different dimensions, and then I look at optimizing it. I look at optimizing my objective function, whatever that is. And most important thing is you use certain algorithms to find the model parameters which would optimize, and one such algorithm is the gradient descent, which all of you would have come across. We will study that in detail in this course. So you use algorithms to get the parameters which would optimize the objective function. So the question is, when do you stop the algorithm? Is it going to be error, is it going to be number of iterations and so on. And the point is, like, you might also want to know whether there is going to be a maxima or a minimum at all in the first place. So you probably get into, we will also do all these ideas, right, okay. And most important stuff is this optimization that you look at. It could be a completely unconstrained optimization, that means there are no conditions at all, there are no constraints at all, just optimize, find the maxima or minima. But typically that is not the case, right. See, it could be let us say I want to reach my workplace, let us say I want to reach my workplace from my house, let us say to let us say IISc. Now what I would say is, like, I want to reach from my house to this workplace, the constraint is maximum travel time is not going to be greater than I would say, like, optimize the travel time, condition or the subject to the constraint that the cost is going to be minimum. So what is the transport that I take? So you could have a constrained optimization or you could have an unconstrained optimization. Constrained optimization basically puts you in a, what do you call, within certain constraints or certain boundaries with which you need to work. So we will be studying optimization, constrained or unconstrained. I gave another example there. If you look at from the perspective of students, it is always like you say minimal efforts and maximal gain. Then you could actually see many of the students end up preparing at the last moment for the exam, and then they would still want to get maximum marks. So that is a kind of optimization problem that people look at. So yes, so we are going to look at all these ideas. We may not be able to look at it in detail. Wherever we could do it in detail, we will do it, and wherever we will give a very holistic perspective, we will do that. And this is again going to be more a conceptual approach, where we will automatically come to the idea of what is the mathematical equation that comes there. So that is something which you are going to look at. So It is not going to be heavy on proofs or anything, we are just going to look at you are going to use common sense, you are going to just get the idea of the concepts, right. Okay. So, how is the course organized? Basically you would have seen that in the website, like what are we going to do. The first 4 weeks correspond to the topics on linear algebra. We will not be doing the system of equations and linear system of linear equations and so on. We would directly want to get into the idea of vectors and vector spaces and subspaces. Typically what we do is we teach system of equations, linear equations, and then look at the solutions to system of equations, and then move on to the idea of vectors and vector spaces and subspaces. But we also have a time constraint for us to put all these topics, and therefore we thought we would start with vectors, vector spaces and subspaces. We would be bringing in this idea of linear equations, system of linear equations and solutions wherever that is required in this 4 weeks of linear algebraic topics. So, the first week will be on vectors. So, what is it to say a vector? Can we have a vector, is vector something associated with the magnitude and direction, or is it an abstract quantity where which obeys certain rules. So, those things we will be studying. We will look at vectors, vector spaces and subspaces. How do you construct vectors, like what are vector spaces and what are subspaces? What is it to say how do we construct vector spaces? We look at all those ideas in the first week. The second week talks about the transformations that you can do on vectors, like suppose I mean you would have studied a lot of transformations even before this course. You would have studied like rotating a vector or stretching a vector, right. You would have studied all that. So, what are the things that we can do on vectors? That is where we get into the idea of linear transformations. And most important ideas about this after this linear transformation is the idea of eigenvalues and eigenvectors. See, not every vector if you take a particular linear transformation, or if you take a particular operation that you want to do on a vector, the vector may not change its direction. Typically when you do linear transformations, you might have vectors to get reoriented themselves, it could get transformed to something else. But there may be some vectors which would say, look, I will not change whatever you try to do with me, I will not change my direction at all, I am going to not get reoriented at all, I am going to be this. And that is where we get into the idea of eigenvalues and eigenvectors, and that is where we look at what are called as invariant subspaces. Week 3 of the course will be on orthogonality, projection and real symmetric matrices. I already told you the idea of or the notion of projection, how important it is in dimensionality reduction and so on. We will look at orthogonality, because we want to look at if there is a similarity between two vectors or not, or they are completely orthogonal to each other, like they do not have any similarity at all. And the most important idea from this week is going to be the idea of real symmetric matrices, because later we will see that the covariance matrix which we study would be all real symmetric matrices, and we need to therefore know the ideas of real symmetric matrices. Week 4 will be on singular value decomposition, another very interesting topic of linear algebra. We look at principal component analysis and support vector machines and applications. And that with the applications we conclude the topics on linear algebra. The 4 weeks of journey into linear algebra gets over, and we embark on another journey from week 5 to week 8 on probability and random variables, where the first week will deal with probability foundations from events to Bayes theorem. All of us would have studied in our high school, and probably in college also we would have studied what is a sample space, what is an event and all those things. We would have done it in the definition way. So, what we are going to do is we are going to look at a lot of insights, and we are going to base our study through insights. We are going to look at concepts here again, concepts yielding your equations. We are not going to focus on, as I said, proofs and stuff. So, we are just going to tell you how this is. We are going to see, like, gradually in the course of lecture we will find that, oh, this is the equation that should be there, and this is exactly the equation that has to be there. So, we are going to look at something like that. So, we start with events, we look at conditioning, we look at Bayes theorem, we also look at independent events and so on, and we also give the interpretation for such things. Most of the times what happens is this interpretation matters a lot. When we do independent events, we just say P of A intersection B is equal to P of A into P of B, but what that actually conveys And those are the things that you will be seeing, the insights, as I said, conceptual insights we will be studying here, we will be doing here. Week 6 will be on random variables, moments of random variables. You look at discrete random variable, continuous random variables, and then you look at what is mean, variance, etc. of these random variables, and what are the moments of these random variables, and so on. That means the behavior of a single variable, single random variable is what we are going to study in terms of probability mass function, probability density function, or it could be a cumulative distribution function. And we are also going to represent, or we are going to study the random variables through the moments of the random variables too. Week 7, what we are going to do is we are going to look at jointly distributed random variables. This is very important because most of the times random variables, I mean you have, so you take multiple variables, all these fellows occur together, and what we do is we want to find out how they behave jointly. See, it is like saying there is a kid at home whose behavior is there, which could be captured in terms of a single PDF, PMF, CDF, or in terms of his moments or whatever. Now what I want to do is two kids are put together in a house, and how is their joint behavior going to be? How are we going to characterize this joint behavior? And are we going to say that, okay, if this kid behave like this, does the other kid, what is the probability that the other kid also behaves something like that? That is exactly where we get into the conditioning of random variables and so on. And week 8 we are going to look at certain inequalities and limit theorems. Inequalities we are going to look at Markov and Chebyshev inequality, which talk about tail probability. That means I want to find out what is the probability of a rare event kind. When I say tail, it means it is beyond certain value, so I am going to look at rare events. Rare events have lower probability, so I want to look at that. And then comes most important topic, which is the sample geometry. In sample geometry we are going to bring in the idea of again matrices, vectors, and so on, and we are going to look at how do we calculate standard deviation, mean, etc. How do we interpret the mean as a projection, then the standard deviation as the length of the deviation vector, and so on. We are going to look at that. And towards the end of week 8 we are going to look at covariance matrices and properties. Once we complete this journey, we get on to multivariate calculus optimization and applications. Week 9 we start with Taylor series, partial derivatives, chain rule, gradient, Jacobian, and Hessian. These are like very scary terms that you would have seen, but these are pretty interesting things to work with. So Taylor series, where you are going to approximate a function, then partial derivatives, when you have a single variable you actually take the derivative with respect to that. When you have multiple variables, a function of multiple variables, you look at the partial derivatives. That means you want to look at the rate of change of this particular function across multiple directions, or with respect to multiple variables, and that is exactly where we get into the idea of partial derivatives. Then we look at the chain rule, which is as applied to your derivatives. How do we do that with partial derivatives and so on. Then the collection of partial derivatives, which you are going to put that in a vector form, you are going to call that as gradient, and then you have collection of gradients, you are going to call that as Jacobian, and then we are going to look at, so basically gradient is the first derivatives, and then you have we want to look at, you remember when we said we want to find out maxima, whether it is going to be a maxima or minima, we do the second derivative test in case of single variable. Now in case of multiple variables we want to find out, do the second derivative test again. So what we do is we look at the Hessian, and we look at certain properties of this Hessian, which will tell that, okay, if this happens, therefore you will have a maxima, if this happens you will have minima, and so on. Week 10 is something again very interesting, where we are going to talk about matrix derivatives. That means I am going to treat a matrix Ax equal to b, I am going to take b as a function which is going to be a vector valued function. I am going to have Ax. So when I have a b is equal to Ax, say a is m by n and x is n by 1 and b is m by 1, that means I am going to say that, look, I am going to have function m valued m functions. I am going to say we have m functions, and then m functions are basically of n variables, each function is of n variables. Now what I can do is I can find the derivative of each of those functions with respect to each of these n variables and so on. So I will be looking at matrix derivatives. That means I can take my matrix and take the derivative of matrix, and that leads us to a very interesting ideas, where we will study the matrix derivatives and then come back to this idea of Lagrangian, and then use it to find least squares and principal component analysis. That will involve a bit of rigorous mathematics. We will also look at the ideas of gradient descent and stochastic gradient descent. we will look at, as I said, constrained and unconstrained optimization. Then what we do is week 11 we will deal with neural nets, perceptron, backpropagation algorithm, and week 12 will be on algorithms for ML, basically classification, clustering and regression. So, in the whole 12-week thing, it will be week 1 to week 3 and a couple of classes in week 4 I will be dealing with ideas of linear algebra. Then Dr. Ashok Rao will be teaching the ideas of PCA and support vector machines. Then week 5 to week 8 completely will be led by me, probability and random variables, and week 9 to week 12. So, we will be doing, I will be doing week 9, I will be doing week 10 matrix derivatives, constrained and unconstrained optimization, gradient descent, Lagrangian and least squares, and PCA I will be doing. Our TA Gaurav will be doing the stochastic gradient descent and stochastic gradient descent he will be doing. Week 11 and week 12 will be completely done by Dr. Ashok Rao. So, so what we want to do is like we really want to make it very clear that we will this course does not focus on any kind of coding exercises, but as such if you want some help and hand holding on coding, you could actually take the help of our TAs who will be more than willing to help you. So, the course will also the lectures will also be supplemented with visualizations which would help you understand concepts better. So, it's now going to be something like this: we finish, we complete machine learning course and then start doing linear algebra, probability theory and statistics and so on. So, it is basically putting all these things together. So, on that note, I welcome you all to this course on mathematical foundations for machine learning, this 12 weeks lecture series that we have. I will be starting the proceedings of this course on vectors and vector spaces in the next class. Namaste.